Hi, my name is Nathaniel Hanson.
And my name is Aryk Ledet.
And we are your lead instructors for the Autonomous Air Vehicle Racing course. This course provides a holistic introduction to unmanned aerial vehicles, more commonly known as drones. Throughout the course, you'll be challenged to think deeply about the complexities of software systems needed to operate an autonomous platform. The course begins with an introduction to UAVs. We examine the electrical, software, and aerodynamic characteristics of our platform and discuss the trade-offs involved in building systems suited for a variety of use cases. You'll gain experience in building and debugging code using cutting-edge robotic software and simulation.
Building on that knowledge, we'll then venture into the field of computer vision. We'll leverage onboard sensors to process visual cues from the world around our drones. We'll need this to detect and avoid obstacles as well as read QR codes. Underlying all of this is the mathematics of stable flight. We'll dive into a bit of control theory and write code that will be used to guide the UAV toward goals in a challenging environment. All these topics converge into a single challenge, a choose-your-own-adventure project, where each team will have the opportunity to show off what they've learned. As we've discussed in the course, UAVs have a unique opportunity to make a difference in people's lives. We look forward to seeing the creativity in the real-world applications of your projects.
All right, everyone. Welcome to the final event for the 2022 Autonomous Air Vehicle Racing course. As you just saw, my name is Nathaniel Hanson, and I am the lead instructor for the course this year, along with Aryk Ledet, and a wonderful assortment of other instructors and teaching assistants who have done an absolutely phenomenal job this summer in building a fundamental knowledge of autonomous systems in these students and helping them along the path to developing some really cool challenges, which we're going to see along the way. So I wanted to just first shout out and say how incredibly proud we are of all of the students. For high school students to be able to come in and to master the concepts and demonstrate them on a real platform is absolutely commendable. I know for speaking personally and for a lot of the staff here that we weren't doing anything nearly as cool as this when we were in high school, except with Remaisa as an exception since she is an alum of this course. But we are so immensely proud of everything that you've accomplished in just one short month. We know there's been a lot of late nights, a lot of head scratchers, and a lot of banging your head against the keyboard to make your virtual machines work with these drones. But we thank you for your patience, and we thank you for all the time and dedication and long hours that you put into Zoom. We hope that in seeing these final presentations, you'll be very proud of yourselves, you'll be proud of your teammates, and you'll be proud of everything that you've accomplished this month. I'm not quite sure where Aryk is at the moment. Maybe he might be having some technical difficulties. So no worries, we'll go ahead and press on. So first on deck for presentations, we will go ahead and get started with the autonomous agents.
Okay, so to open up this presentation, this is BAVCAV brought to you by the autonomous agents. I'm Andre.
I'm Phoenix.
I'm Aditi.
And I'm Paul.
So BAVCAV, standing for Body and Voice Controlled Aerial Vehicle, started off as an idea to control a drone using simply hand gestures. But after a whole week of work, it's become so much more. Right now, BAVCAV is a system that allows a user to control the drone both with hands and through vocal commands. Currently, the drone is able to execute various commands such as simple movement, geometric movement, tricks, and photography. So in the end, this allows people with speech impediments or perhaps mobility issues to control the drone hands-free with full functionality. To enable us to work on this project, we use a series of tools. The first one would be ROS, which stands for the Robot Operating System, which allowed us to organize the project in a more understandable and logical way. We used media pipe for hand recognition, as you can see here. And the last three, which are speech recognition, PyAudio, and Pocket Sphinx, enabled us to actually get voice recognition, as you can see here. The hardware we used were simply the Tello, the drone, a headset to actually recognize voice commands, and hands and vocal cords to communicate with the drone.
So here's our robotic operating system architecture. So the way this works is that there's three key nodes: driver, movement, and sensor processing. So sensor processing gets all of the input, the visual and audio inputs, which are the hand gestures and voice commands. And it will send those commands to the movement node, where the movement node will take the command and then sends the velocity to the driver node, where the driver node will send everything to the drone. So here's a list of some of our modes and commands. So for simple movement, we can have the drone move in 6 degrees of freedom. While tricks, we can have it do flips, we can have it fly up and then free fall. We can have the drone move in a wave or bounce or spiral. We can have the drone move in various geometric shapes. We can have the drone target and follow the target, or fly at the object for the target mode. And then for photography, we can have the drone take photos, record videos, and save those directly to our computer. So the way we implemented our hand gestures is that we use a combination of what finger we're using and direction. And using those two parameters, we were able to come up with 128 different combinations, but we've only encoded 25 different gestures and linked them to each specific commands.
So to implement the vocal commands, we used a headset that's connected to your computer along with Pocket Sphinx, which is a voice recognition tool. And basically the way this works is we were able to create a dictionary of words that the drone is able to recognize. And we have a picture of a couple of those commands here. On the left, you have the command, and on the right, you have the phonetic spelling of it. And what the drone does is it listens to your speech from your microphone, and it finds the closest match to the dictionary words. The way you do this is you say the keyword command, and it'll listen to whatever you say afterwards, and then execute that command. And here we're going to have a short demo of our drone.
Command start. Command down. Command backward. Command up. Command forward. Command. Command down. Command. Command square. Command.
So we faced many challenges when working on our project. One that initially popped up was with the voice recognition, which it was really challenging and took us a long time to figure out, mainly because we were originally using a tool called Google API, but later realized that we couldn't have it work simultaneously with the drone. Even after switching over to Pocket Sphinx, the drone took a lot of adjustment to be able to be responsive enough to move smoothly. We also faced a couple challenges with the scope of our project because we originally had very lofty goals. We wanted to feature facial classification, but we had to cut the idea due to time constraints, and that's something we would potentially work on in the future. We also originally wanted hand and gesture recognition to use a machine learning model that we created, but that's really complex and it would take a lot more time than we had. So instead we used MediaPipe to just recognize the gestures and of course link them with the certain commands. Another problem that popped up with us was with the follow function because it required the drone to know its distance from the user, and that was very difficult for us to figure out how to retrieve.
Despite these failures, we kept pushing and worked as a team. Specifically, for any feature, we would gather everyone's ideas, even if it was not their assignment. And through all these ideas, several pieces of our code were made simpler and brought to fruition because of people who weren't working on that process. So it really does take a team to get to success. We also realized how quickly things get done when no one is left in the dark. I personally felt this when I understood what I was doing more. I felt like I was able to contribute more to the process. And as a result, the drone now features almost flawless gesture and vocal commands without the need for memory-intensive processes such as machine learning. For future work, we would need to enable the autonomous portion of the drone by getting the follow function to work to fly towards and with the user. Currently, we have the tracking portion working, but the follow portion is not working. And to continue off this project, we would need to use machine learning in order to recognize both faces and objects, both to respond based off of a primary user or not respond based off a stranger, and to respond based on certain objects and obstacles. Thank you for listening. I hope you enjoyed this presentation, and I hope you enjoyed this beautiful photo that the drone took of Andre, just as much as we enjoyed spending our time working on this. Are there any questions?
Yeah, we'll ask. There's a couple questions in the chat, which I'll go ahead and pass on to you. So the first question is, how long did it take to process each of the hand signals that you were tracking?
So it's actually a really fast process. Just the hand tracking program is actually really fast. Like it can track the hands live. But as you saw in one of the slides, if we go back, if you try drawing the points like we do here, it actually slows the program down significantly. But for the purposes of our program, we don't actually have to do that. So it's actually really fast and tracks hands in real time.
All right, very good. Go ahead.
Oh no, I was asking, are there any other questions?
Yes, one other question. So you mentioned that the distance following would be or following a person would be the next step that you would do. What would you need to do to make that work?
So originally the biggest point of our goal was to get the drone to follow us, right? So you can just basically tell it to follow, and it will center you in the camera and fly towards you as you walk away from it. To do that, we would have to get the distance calculation. As we said, we don't have the sensors equipped on the drone to do that. We actually came up with a solution that we didn't have time to implement. We would use several of the points on the hands to calculate the distance of a specific finger, right? And once you have that distance in pixels, we would compare that to the actual scale of a regular finger in real life, and then approximate scale of the rest of the image, and calculate the distance like that using just simple trig. Any other questions?
No, that looks like it's it. So thank you so much, Autonomous Agents. We love the hats and the team spirit as well, as much as a phenomenal presentation.
Thank you.
So great job. And next we will go ahead and swap over to Team Buff Bobas.
Hello, we are Team Buff Bobas, consisting of me, Alex, Jaden, Ishan, and Adrian. Imagine you're sitting there at your desk vibing to some song, right? And you have this feeling that you want to vibe harder to the song. We have the perfect solution for you. So with our incredible Tello technology, you can dance with a friend for around 13 minutes. While friends may be a foreign concept, at least to me, it'll be an incredible experience with what we are about to show you.
Okay, so essentially our project is to create a Tello drone that can dance to music. And to do this, we plan to integrate various Python audio libraries for the computer to recognize the tempo and beats of a song. We plan to create a user interface to ask the user to create simple dance moves through drawings such as lines, curves, and geometrical shapes such as squares. Once those are taken care of, we need the drone to take off and execute the dance sequence synchronously on beat with the music playback. And we also need to a list of pre-created dance moves such that if the user doesn't input any moves or inputs too few moves for the tempo, basically the beat of the song, it would rely on those pre-created moves.
So in our project, we use a variety of software and Python libraries to bring our program together. Most notably of these libraries were Librosa and Pygame, which are both major components of our pre-processing. Librosa was used to extract basic features from the music, such as the tempo and when the beats of the music occur. Pygame was used to create a user interface through which the user could draw the dance moves. This library also served as a music player. The DJI Tello Pi library was also used to connect to the drone and send it movement commands. The time library was used to properly synchronize the music with the dance moves, and NumPy was used to work with the music beats and analyze the drawing input. We also had plans to integrate the robot operating system, better known as ROS, in order to interact between the drone and the scripts in real time, but we'll explain later why this didn't quite work out. And as for how our code worked, we had three primary components: the music input, the drawing input, and the driver. For the music, the user would be prompted for the name of the music file, the number of beats per measure, and whether or not the song had a pickup beat. With this information, the music node would process the music to approximate the tempo, the beat timestamps, and the beat durations. This info would then be relayed forward.
For the drawing input node, first the user would click a button to indicate what type of move they desired, such as a flip, a linear movement in the XZ plane, or like facing the user, a 3D movement, which was forward and backwards for the user, or a curvy movement. And on top of this, they would draw a single line stroke to indicate the direction and length of the movement. So as you can see in the bottom, there's an example of one of these inputs. The green is the starting position of the user where he clicks the mouse, and the red is where he lifts up his mouse. And as you can see, this type of stroke is equivalent to a movement in slightly diagonal to the top right. Another example would be if this user drew the same exact stroke and chose flip, it would flip towards the right because it is a stroke starting from left to right. So after we got this input from the user, we would then convert it to a dance move through Tello commands such as go XYZ speed, curve XYZ speed, or flip direction. And finally, this would be sent to the overall input node. However, our robot operating system, which is ROS, did not work out as we planned. So what happened was the ROS and running the extra nodes on top of ROS made the Pygame too slow for user input, and essentially made it so that when the user tried to make a line, it would operate at less than a frame per second, which made it pretty much impossible for a user draw input. So we had to switch it over to a Python script outside the virtual machine. And on top of that, we were originally going to create a machine learning network that could identify shapes that correlated to moves, but time constraints did not allow us to do that.
And another challenge that we had was initially we were trying to use a library called Pi Audio Analysis to recognize the individual bass notes in the song, but this turned out to be a lot more complicated than we initially foresaw, and so we instead had to resort to using the rhythmic information in the song to execute the dance moves. And initially, the Tello was not dancing on beat due to the Wi-Fi and the lag over the Wi-Fi. So instead, our fix for this was to make it dance every measure to give it time to catch up and not give it too many commands too quickly.
This is a demo of our drone dancing along to the song Baby Shark. The first part will be the user giving in the input, and then the second part will be the dance.
Daddy shark, do 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 do, daddy shark, do 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 do, daddy shark, do 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 do, daddy shark.
Grandma shark doo 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 doo. Grandma shark doo 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 doo. Grandma shark doo 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 doo. Grandma shark.
Grandpa shark doo 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 doo. Grandpa shark doo 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 doo. Grandpa shark doo 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 doo. Grandpa shark. Let's go hunt doo 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 doo. Let's go hunt doo 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 doo. Let's go hunt doo 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 doo. Let's go hunt.
Run away doo 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 doo. Run away doo 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 doo. Run away doo 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 doo. Run away. Safe at last doo 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 doo. Safe at last doo 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 doo. Safe at last doo 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 doo. Safe at last. It's the end doo 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 doo. It's the end doo 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 doo. It's the end doo 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 doo. It's the end.
So here were some of the takeaways and future additions we would do if we had more time for our project. So for our takeaways, even though we weren't successful with this, we were able to do a deep dive into ROS and learn how it can be integrated with different programs and code to make one functionable workspace. We explored and learned how to use Python libraries such as Librosa, Pygame, and DJI Tello Pi. And we learned how to effectively utilize GitHub for team projects. Possible future additions, if we had more time, we could do the implementation of melodic information of the song to control the Tello. What this basically means is that because there's a lot of time consumed from the Tello or from the user to the Tello to relay the dance moves, we had to lengthen the amount of time from each dance move sequence. So if we could somehow shorten the amount of time, we could make the dance moves in a much quicker sequence. We can use Aryk tags or AR tags to keep the drone centered in the room. We faced the issue that oftentimes when the drone was done dancing, it would often drift to one side or the another, causing it to hit a wall. So if we had Aryk tags, we would allow it to be centered perfectly in the room. And another future application is we could add more drones so that it looks like a swarm, which would allow you to vibe harder to your song. So yeah.
Thank you very much for listening. And is there any questions?
Excellent job, Buff Bobas. We have a couple questions in chat, so I'll go ahead and ask the first one. So I think you said the question is specifically about time signatures and like the number of beats per minute. So are you able to handle a changing time signature? Because obviously like the music can speed up and slow down. How do you handle that in the music?
So we're able to handle that because the way that we extract the beat information is that we extract the time of each beat, not the tempo. So if the time signature does change, if the tempo does change during the song, then we'll be able to account for that because we're extracting when each beat is happening and not just the tempo. So yeah, that's how we would account for that. And the time signature, currently we're not able to account for that changing in the middle of the song, but we are able to have a preset time signature when you input the song so we can account for like odd time signatures throughout a whole song, but not changing.
So there is another question, which was how fast can your drone react to the beats? Or also a similar question to this is what is the lag between the Tello command and you executing the drone to move?
We don't have an exact number, but it does react pretty slowly. But we accounted for that by including like different buffers on the dance moves and stuff, so it would be able to react in time with the music. And if the tempo of the song happened to be too fast, we would slow down the pace of the dance, so it would still be able to react on time.
We got a couple of questions about song choices. So one question was, what is your favorite song that you had the drone dance to?
I'll say it wasn't Baby Shark.
And then the last question was, what made you choose Baby Shark?
We decided to use Baby Shark because it was a fairly normal tempo, but it also has a tempo change in the song. So we use that to test how the drone would be able to react to different tempo changes, and it seemed to work pretty well. So.
All right, excellent. I think that's it for questions.
Yes, excellent job, Buff Bobas. Love the dance moves, but we'll go ahead and move on to Team Herd.
Thank you very much. Hello, everyone. My name is Camden Bartlow, and I am here with Team Zeroth Responders, presenting our project, Herd, the Home Alone Emergency Response Drone. Now, speaking of the Zeroth Responders, here are my stellar associates. Of course, there's Camden Bartlow, me.
I'm Russell Castro. And there's Zion Reiki.
All right. So our project is attempting to deal in a drone-related solution to a real-world problem. And very generally, lives could be saved if emergencies could be detected and acted on sooner and at a more immediate level. And specifically, our project aims to remedy the already high statistic, that is the number of older people across the United States and across the world, really, that fall down and suffer irreparable damage as a result. And that statistic, it was already high, but it is on a steep increase, as we could see by this CDC graphic right here that shows the actual death rates with falling with respect to the year, and it has increased. It was already high, but it has increased. And so this is a real world problem that we thought drones could help remedy. And now we're to explain how with our solution.
Yeah, so as for methodology, we process audio signals received by a global mic to distinguish thuds. We then navigate a route to determine the source of the thud, which could be a fall. As the drone scans around rooms, we use onboard vision on the drone to determine if a human has fallen.
In terms of the actual audio signal processing aspect to our project, there are two parts. One is the thud detection and the other is voice recognition. In terms of thud detection, we use audio signals as an input into the standard deviation, into basically a standard deviation algorithm, which processes the audio signals and determines whether a person has fallen or not. The reason why we use standard deviation over other statistical means is because, well, first of all, we didn't have the time to implement a full-blown machine learning model, and also using standard deviation, we were able to consider spikes over a period of time rather than individual spikes. Secondly, the second aspect to our project was voice recognition. So the reason why we implemented voice recognition is because it gives the users control over the drone if it malfunctions. For instance, if the program is unable to detect that a person has fallen, just by saying the word emergency, the drone will take off by itself.
For drone navigation, the drone approaches rooms from a central home position, and on a predetermined route, using Aryk tags to localize its position, the drone uses tuned PID to position the drone for scans.
For human detection, you can see the images off to the left. So, of course, if we're detecting human beings that have fallen onto the floor, a downward-facing camera would be entirely ideal. And luckily, the Tello drone that we were equipped with by the UAV course did have one. So we were very lucky there. And OpenCV's HOG, the histogram of oriented gradients, proved very useful in our ability to detect objects. It is an object detector, in our case, humans. And we use this as a sort of way so that detecting humans would not be the thing that would consume our time, but optimizing and customizing the HOG, I love that acronyms, the hyperparameters would be how we spent our time, making sure that it could detect humans with great accuracy and certainty, but at the same time, not take too much time and not prevent us from doing anything else. And here's the fun stuff. The problems I encountered with my group as we were moving through this OpenCV human detection was HOG's preferences with human beings and its typical usage not being looking for people that had fallen onto the floor, it being sort of detecting passersby on the streets from like cameras that were decently far away. And so if the drone was too close to the human, it would not work as efficiently and accurately as it would had it been a little bit higher up. And we made sure to plan accordingly. And accessing the Tello's two cameras simultaneously as our drone needs the front forward-facing camera to see the Aryk tags, essential AR tags that are placed around the room so that we can find where we are and move around. and using the bottom one to detect human beings. The Tello didn't allow us to access those two simultaneously, but we created a rather fast swapping mechanism in the code. In the images over here, you can see that the hog can detect a human, me, laying belly up, belly down, and belly off to the side, which is very awesome because we want to be able to detect humans no matter what position or posture they are in. And this is just a for fun image of early testing where you can see that we came a long way with the green noise down here and the human not being too close to the center of the body. And yeah.
Yeah, so here I will be presenting our project demo. So initially the drone starts off by taking off from a central location. It then localizes with a central Aryk tag. Then it turns and flies and localizes onto a door-centric tag. From there, it scans the room in quadrants, looking for fallen humans. So here are a couple images of the scans. And here on the fourth one, it sees one and it notifies the system.
As for future improvements, this is a solution to a real world problem. So there would be a lot of things that would need to be done, have real world implications. For starters, more efficient pathing and navigation of the environment would be absolutely essential, as if a person has fallen, we want to get to them as soon as possible and search for them and emergencies in the most efficient and non-time consuming way, as that could really make a difference. And so creating a method of going around a house that is not a set path, but instead more vectorized would be monumental. And SLAM, which stands for simultaneous localization and mapping, would be crucial for having the adaptability to put this in many different environments, places, settings, and have it work all the same. That could work with the more efficient pathing, and together the amount of time and the amount of implications that this solution could have would be astounding.
The third improvement that we think we would benefit from would be better and more realistic thumb detecting. So as I said before, in terms of the audio signal processing part, we weren't able to create a machine learning model to do this. And if we were, we'd be better able to classify sounds as thumps and identify when people have fallen or not. The fourth improvement is finding a way for the drone to not heat up when not moving. So what happens is that the vents of the drone is located on the bottom. So even when the drone is not moving, it has no way to disperse that heat. So ultimately it heats up.
Yeah, so due to the limitations of our platform, as Camden had earlier mentioned, we had trouble getting simultaneous forward and down camera streams. So that would be something we would look into to improve our products. And as of now, our solution for the detection is imperfect, as it only uses one mic globally, independent of the size of the home, which could give us trouble as homes change size and conditions like flooring or like a door being open or closed change. And that can overall just hinder our threat detection. Also a big one, what if a door isn't open? So we have looked into having the drone pass through windows and vents, but currently that is an area for us to work on after the program.
Yes, and another solution to a door not being open would to have, together with the human-robot interaction with the sort of hub of the drone, to tell it to stop, tell it it's an emergency, have it malfunction. We could have a speaker that says, this door is not open, there could be an emergency. In the next 30 seconds, if I don't get a response, there will be an emergency. So our team has discussed a true number of solutions to that very fundamental problem for its real world implications.
Thank you
all very much. Are there any questions?
Yeah, there's a couple of questions in the chat. So I'll go ahead and ask the first one, which I think handles a couple, is why didn't you use machine learning for the person detection?
So we used, of course, open source computer vision's hog descriptor, but mostly the reason we didn't create our old model would be the time constraints. There are a lot of different each essential components of this product or this project that needed a lot of time, love, and care. And so we knew that a human detecting machine learning model would be awesome entirely, but it may not work with our time constraints. And so using OpenCV's built-in hog descriptor human detector was really worthwhile, I'd say. Any other questions?
Yeah, a related question to that is, did you ever have to deal with false positives or false negatives when using Hog?
So luckily, it doesn't just give us rectangles representing humans' bodies. It also at the same time returns the likelihoods of it being a human being. And so while there were times, especially when we, to solve the switching between cameras problem, there was a time when we solved that problem by looking only out of the forward camera looking for humans, but that introduces a lot of noise that projects things like laundry hampers. That's actually real as 100% being humans. So the probabilities of being humans was something that we used to ensure that if it was over a specific threshold, that would count as a human. And in the images that you saw back there, I'll actually go back. Oh boy. Those were examples where I said, take the most likely human in the image and only display that rectangle. So we used the likelihoods that it returned as a sort of way of detecting what is a human and what is not, and also using the downwards camera so that crazy noise, like noise that was almost indifferentiable from a human being, would not be included. I think that's just.
We have another algorithm-based question, and this, you kind of touched on this. How does your algorithm handle noise? But they have a specific example of the person being covered or surrounded by clutter.
So that is entirely essential to our product. So it's a great question. And of course, using the downwards facing camera, a lot of things look really not human when we're looking down on them. So handling noise is definitely really helps by that. But at the same time, if the person is covered, had they fall, that is very unlikely. But if they are covered, we have seen, I'm very sad I didn't include it, but I have images of humans being covered, but still detected, like if half of their body is behind a chair, I fell like sort of like at an L posture behind a chair, it was able to recognize me just by the top half and bottom half of my body. So it doesn't need much to tell if a human is a human, but if the entire body was covered, that would be a real problem that we would have to solve in the future.
Okay, excellent answer. Excellent job. And we're going to keep moving. So next up, team Just Fly.
All right, so let me quickly screen share. Okay, we are team Just Fly, consisting of Riva, myself, Aryk, and Anna, and our product name is Just Drone.
So we wanted to code something that could create a dancing drone that could follow the characters in a Just Dance video to autonomously play the game. Autonomous tracking of colors can also have lots of other applications, such as movement to follow an object in real life.
Now, for those of you who maybe aren't as familiar with Just Dance, the neon-colored hand of the dancer on screen is where the player would hold the remote, and therefore that's what we want the Tello to track. So in order to find the hand, we use color segmentation and then PID controls to follow the hand's movement, which we'll expand on later. And we also found and drew the contour of the TV to make sure that the drone stays a set distance away from it and is also perpendicular.
We also wanted to make this project as accessible as possible to the user. So we created a color picker so that users can pick the color of the hand they want to track so that they can use our code with different songs. And we also included a feature to input the dimensions of the TV and the distance the user wants the drone to stay away from the TV so that the drone can take the corners of the TV we detect and stay a set distance away.
For our program, we ended up using a variety of libraries, some of which includes the DJI Tello Pi one, which we use to move the drone around. We also use ROS, which stands for Robot Operating System. And this is a piece of middleware that makes communication between our programs and our scripts, as well as with the hardware, which is the drone, far easier. We use OpenCV, which is a computer vision library for segmentation and scanning. And we also use PID controls, which uses the difference between the target position and the current position, the error, to accurately move the drone around.
Onto ROS, the most important piece of our software. With ROS, we were able to divide our code into separate parts called nodes, which could communicate with each other by sending messages, providing a framework for our project. We used a startup node that ran the color picker, a driver node that controlled the drone and sent images from the drone to the hand node, which then segmented the image to find the center of the hand and sent back a command to move towards the hand. And the driver node sent the image to the TV node, which could then figure out where the TV was and send commands back to the driver for how to move to stay within the position ranges for the TV.
And now here's a little demonstration of our code at work.
When I roll into the live it up, give it all you've got, make the party.
Call me hoppy, anything baby, just not sloppy. Floppy ears or point it up. The part is for us, so don't disrupt. If crap gave a damn about us rabbits, you'd have it, go grab it. Carrots in the hat, but not a cat. I jump the spot like an acrobat.
Your heartbeat dances to the sound unbroken melody. It's crazy, baby, looks so good. Don't mind if I creep up on you. Can be chained to a dream that fools our hearts, so sit down, shawty. Together we can make this dream come true, so let's break all the rules.
Something brand new. I'm in love with the shape of you. Come on, be my baby, come on. 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 Come on, be my baby, come on.
Call me maybe, and all the other boys try to chase me, but here's my number, so call me maybe. You took your time with the call, I took no time with the fall. You gave me nothing at all, but still you're in my way. I beg and borrow and steal at first sight, and it's real. I didn't know I would feel it, but it's in my way. Your stare was holding, ripped jeans, skin was showing, hot night wind was blowing. Where you think you're going, baby?
What I go through till I find you. Every minute I'm without you, without you. 'Cause an angel touched my heart and took my cool. Every second burns like fire.
I find you.
So while working on this project, we came across a variety of problems. One of the big ones being that the telecamera was kind of subpar, as some of the parts of the image got blown out, and we also had problems with implementing our parts of our code into ROS as we got errors. We also had problems with sometimes segmenting the wrong thing. For example, sometimes the arrows were the same color as the hand, so then they would be included in the filter as well. Though with a lot of testing and trying out different things, we were able to get a lot of these things fixed. For example, with our ROS issue, we took separate parts of our code and we tested them separately, trying to integrate them one at a time. With our hand segmentation, we made our color filter a little more strict so that it would try to filter out the arrows and just keep the hand in. And we also used Gaussian blurring so that it would smooth out some of the errors, so it would make it easier for us to detect the TV so that the drone could stay inside.
And now here's another video that shows the parts of our process that were caught on camera.
Okay. No, my Tello died!
Oh my god.
This is tougher than I thought.
Oh my god, I think it's working.
Oh my god, the Tello video is absolutely horrible. How are you supposed to see a hand in mid?
Data quality at work with edge detection.
Oh, you gotta film this.
Okay, so now on to a few of our future developments. So after this program, we hope that we can improve our program by making the Tello automatically take off and land through various sensor inputs, or if other things such as sound is heard. We also plan to implement a better way to remove glare on images for better scanning, and we hope to be able to attach a Joy-Con controller to our Tello and have it actually play the Just Dance game. And lastly, we also hope to add LEDs to Tello and maybe make it even change colors based on the music's tempo or rhythm. Okay, and thank you everyone for listening. Are there any questions?
So I just had one quick question. So specifically, it looked like in the terminal that you were sending a lot of commands to the drone, assuming like every time you got a new frame, you like updated command. That ever like flood the Tello with too much information?
Yeah, it was a lot of information. And sometimes it would slow down the drone a little and give it a bit of a delay. But most of the time it worked pretty well, and we had to add in code for it to only take in images a few times a second so that it wouldn't overflow.
Okay, very nice. We're a little bit short on time, so we're going to keep moving on. But thank you, Just Fly, for those really high quality videos and a really high quality project as well. So next up, we have Team Mad Hatters.
All right. Hi, everyone. So because one of our team members can't be here today, we'll be playing a recorded version of our presentation, but we will answer questions at the end.
Hello, everyone.
We are the Mad Hatters. Our project name is Audio Detection and Light Tracking for Improved Queuing Encounters with the acronym ALICE. Our team consists of Yuru, which is myself, Mihika, Maggie, and Anya. Here is an overview of our presentation. We will begin with an introduction of our project objective and goals, and then we'll talk about the components of our code, such as LED detection, PID controllers, etc. And then we will show some demo videos of our final outcome. And finally, we'll talk about our thoughts and reflect on what we've learned. So the objective of our project is to make the process of directing air vehicles more efficient by enabling UAVs to follow light sources autonomously and integrate audio detection to specify commands. Here is an outline of our work process. In Stage 1, the drone was able to detect and mirror light motion. In Stage 2, the drone was able to detect different colors of light and operate in more complex light environments, such as having different brightnesses and having multiple sources of light. In the final stage, we added an audio detection for light color command, so we can tell with voice commands to the drone what color light we want the drone to track. Here is a list of the components of our code. First, we run audio detection, which determines the color of light that we want the drone to track. Then LED detection is called, which detects LEDs in the camera's view, and finds the light that matches the color detected in the audio detection function. The location of the light is then passed on to PID control, which sends commands to the drone and make it move to center the LED on its camera's view.
We wanted to use audio detection to be able to give the drone different commands and tell it to follow different colors of lights. This could be useful in real life if the different LED colors corresponded to different drone actions. All the commands are in the format track and the LED color to track, so if we told it track blue, it should follow the blue light. To do this, we utilize BWSI, which takes microphone input and converts the speech to text. Once we had the text, we looked for the word track, and then sliced the text to find the next word. If it existed, we checked if it was red, blue, or green, and then updated the LED color to follow accordingly.
I'll be touching upon the LED detection code and process. So first, we perform some basic image processing on the image we get from the drone camera feed. We set all the pixels above a certain brightness to white and the rest to black. Next, we use connected component analysis to get groupings. If the component has a sufficiently large number of pixels, so for example, greater than 100, we add it to the mask of large blobs for large components. Afterwards, we find the contours or edges in the mask and then sort them from left to right. We then call the LED color filter function, which sorts these contours into 3 different types of LEDs, red, green, and blue. We loop over the contours, and depending on which light is being tracked, we draw these contours onto the image, and then the program then returns the list of LEDs to track to main. Now, as for the LED color filter function, we were originally going to use RGB values, but this was too unreliable given the darkness of the room. So we switched to using HSV values, a different color system, to filter the contours list, and the function decides the LED color of a contour based on the most common hue value in the image. And over here in these 2 images, you can see the detect LED function is able to correctly identify all the LEDs in an image, and it's also able to selectively choose by color.
When we first attempted to make the drone follow the LEDs, we tried to use optical flow. Optical flow helps us see the motion between frames. Specifically, we use sparse optical flow because it tracks less points on the frame and we thought it would be more efficient for our project. We used many OpenCV methods for this. First, we defined some important parameters, and then we got a frame from the drone's camera and used the good features to track method to calculate some important features, specifically in the area where the LED was. We then calculated optical flow with the next frame, and then took the average between the 2 to get the average horizontal and vertical change between frames. However, we ultimately didn't use optical flow and ended up going with a different method, which we will talk more about in the next.
To control the drone's movements, we will use a PID, or proportional integral derivative controller. And this works in a loop to get feedback from the camera and then calculate actions the drone should take based on the error. And the error is just how far the LED is from the center of the drone. The PID controller will return a velocity value that can be passed to the drone to tell the drone how fast to go and in which direction. So first we'll need to create a PID class and initialize instances of this class. We'll have one instance for left and right motion, one for controlling up and down motion, and one for controlling forward and backward motion. Then we'll define constants P, I, and D, and we'll need to tune these constants so that the error converges to 0 quickly but without oscillating too much. So for each frame that we receive from the camera, we will detect the LED and then pass it to the PID classes. For the left, right, and up-down motion, the error is just the distance the LED is from the center of the image. And for forward and backward motion, we know the size of the LED in real life, and then we can use the camera's field of view to find the distance to the LED. Then we'll get the output, which is the velocity in each direction, and then use the Tello's send RC control function to send the velocities. In this video, we can see that the drone's camera, which is in the bottom left corner, is detecting the LED and circling it with a red circle. After the LED is detected, this information gets sent to the PID controller, and the PID controller uses the distance from the LED center to the center of the camera to determine how the drone should move. So the result of this is that the drone always keeps the LED in the center of its camera and always stays at a specified distance.
This project taught us a lot of new information about ideas related to computer vision. Firstly, we learned about color and brightness detection and identification in OpenCV, such as built-in methods and algorithms. This was used in the LED detection code. We previously considered using optical flow for LED motion detection, which is another useful technique besides PID. And lastly, we studied audio signal processing to determine the color of light to follow.
All right, so thank you for listening. And is there any questions?
Yeah, I can take it. So the question is the drone able to follow LEDs at a distance, or does the LED need to be close to the drone?
The drone is designed to, the code is designed to make the drone to follow the LED at a set distance. So we can basically set the distance to whatever we want it to be. And so the drone would just calculate its distance to the LED and maintain that distance as the LED moves.
Very cool. One other question. What do you do if the LED goes outside of the drone's frame?
In the video, I think there were a few instances where the LED moved out of the drone's camera's view, but in those cases, the drone would calculate from the motion of the LED in its view before the LED goes out of frame, what direction it's moving based on where the pixel shifted. And so it'll move in that same direction to keep the pixels in the center of its screen. And so even if the LED went out of the drone's view, then it'll still go in that direction until it really doesn't see any LEDs at all. Then it'll just stop there.
Right, and then just one more quick question. Is there a possibility your drone can mistake an LED light for another light? So what happens if you have a false identification?
I know we struggled with a lot of false positives in the beginning because our code it identified a lot of bright spots like windows and reflections as LEDs, even though they weren't. So we tried to filter our results by using the shape of an LED, and that helped a lot. And also color, because we're only working with red, green, and blue. So if it's a white light and it's too big, then we're able to filter it out.
right, great answer. All right. Thank you so much for the wonderful presentation, Mad Hatters. I love the creativity. And now without further ado, last but not least, we have Team Tortoro.
Hi, everyone. Thank you for tuning in to the last presentation of the day. We are Team Tortoro. I'm Charlie Benjamin.
I'm Jonathan He.
I'm Roy Yoria.
And I'm Gracie Shan.
And our project is Catkin Bus, title inspired by the popular film My Neighbor Totoro, and Catkin Workspace, which is an important ROS-related tool that made this project possible. So entering the final UAV challenge, we knew we wanted our drone to do something with integrated object detection and path tracking, two incredibly important tools for a new era of aviation. We found the elusive Tortoro and his magical flying cat bus to be the perfect analogy for our project. Tortoro representing the human we will be tracking, and the cat bus representing our navigating Tello drone. But enough about our inspiration, onto the presentation. So today we will be presenting to you in this order of topics. Our project objectives, tools we used, methodology, which includes localization with AR tags, YOLO, frames of reference, PID, and waypoint navigation. And finally, we will end the presentation with a demo of our work, challenges we experienced along the way, and potential extensions of our project.
So here are the steps and tools that we use to build our program. For the physical tools, we have the Tello drone and Aryk markers. As for the software, we're using ROS, Python, OpenCV, YOLO v5 with PyTorch, and RViz. So onto the steps of our program. First, we set up a stationary Aryk tag on the wall and use the driver nodes, which is responsible for communicating with the Tello drone, sends a takeoff command and receives the Tello string. Then second, we find the Aryk tag's position using OpenCV. Then we detect the person's head using YOLO and calculate its position. From this information, we estimate the pose of the drone relative to the head and the Aryk tag. Then third, we compile the waypoint in the form of a queue of the person's head's locations. After that, we use the PID controller to continuously update the drone's optimal velocity to follow the waypoints. And lastly, we have backtrailing, where the drone stores these waypoints in the memory and navigates back to the starting point after all the points have been reached. And onto the ROS architecture. It is made up of 5 nodes, each running on a different thread. So think of them like 5 workers that each specialize in a different task and work together to make our program more organized and more efficient. So the tight integration of these nodes is made possible through communicating different messages among them, like the video feed, the drones and the head's locations, and as well as the velocity command.
Our first node is the localization node. The node utilizes Aryk tags, which are score reference markers that help the drone know its position in a given environment. We will have multiple Aryk tags in our environment to minimize error.
We also use YOLO, which is an algorithm for real-time object detection using neural networks. So YOLO is special because it detects objects in a single run over the image, which results in a much faster image analysis. It works by dividing an image into an equal-sized grid. It then implements bounding box regression on objects on each region of the grid. And finally, it computes a feature map. In our project, the drone used YOLO to identify the person's head and then calculates the head's position relative to itself. And we trained it on the Coco and CrowdHuman datasets.
So here's the setup for our frames of reference. From the localization and YOLO nodes, which we've gone over, we obtained the positions of the AR tag and the head from the observed point of view of the drone. Given these 2 items, we're then able to deduce the location of the head from the POV of the AR tag. We use the position of the head in the AR tag's POV instead of the drone's, because unlike the drone, which is mobile, the tags are stationary, and therefore they're representative of the environment. Now, given all this information, we can then compile a list of the head's locations as waypoints, which are 3D destinations that the drone can follow. Moving on to motion control. So now that we've collected waypoints following the person's head, we need to send velocity commands to the drone so that it can follow the waypoints. We do this using PID, which adjusts the velocity of the drone through a feedback loop that minimizes the error in the position of the drone currently and the desired waypoint.
Smooth trajectories are achieved by tuning the parameters P, I, and D, which respectively apply gain, limit oscillations, and dampen the gain as the waypoint is reached. Here we have an algorithm for following waypoints. We first cue the waypoints to follow in a sequential fashion, tracking the user's head. Next, we enter a feedback loop that compares the difference between the drone's location and the waypoint. The PID controller then determines the appropriate velocities until the drone reaches the desired location, after which that waypoint is discarded from the queue and the drone proceeds to follow the next one.
So as you can see, this is a more detailed diagram that explains waypoint navigation. On the left, we define a queue of waypoints that the drone needs to follow, as shown by the little circles that have H's on them. And each waypoint includes the head's displacement in the X, Y, and Z direction. And then we set the target point as the first waypoint and use a PID controller to determine the velocity of the drone until it reaches the target, which is shown in step 2. When the drone approaches the target is automatically updated to the next waypoint. This process is repeated until the drone traverses through the entire queue. And as a side note, we implement the PID controller instead of the waypoint function built into the Tello's API to eliminate the pauses and make sure that the drone flows smoothly between the waypoints. And if you can play our video demo.
We know the demo looked pretty cool, but it actually took jumping over quite a few hurdles to get there. Our most difficult challenge is that we weren't able to get YOLO to detect heads in real time. The detection algorithm was processing one frame in about 11 seconds. We then got this down to 2 seconds, which was still too slow. Finally, after continuous hours of testing, we were able to have the YOLO detection working at 3 FPS, which is sufficient for real-time processing. As for future extensions, we have been heavily considering the continuation of this project after BWSI ends. Some actions we could still take are optimizing YOLO and PID control, which is how we stabilize the drone while it's flying. We could also add dynamic obstacle detection and an avoidance so that the drone can navigate back along the recorded path, even if there are new objects in its path. Applications include tracking new hiking trails, researchers doing fieldwork, and any other sort of exploration navigation. Basically, the work we're doing here sets a huge precedent for all sorts of research and recreational applications and can be easily built off of. Someday, our code could help a lost caver navigate their way back to the sun, or be used in a project that dynamically analyzes movement. We would like to see these dreams become a reality. Well, that's a wrap up. Thanks for listening. And thanks to the instructors that made this all possible. None of our groups could have done it without BWSI, Aryk, Nathaniel, Ifeiko, both Mats, and Rumesha. We are now open to any and all questions about our project. Thank you.
Great presentation, everyone. We've got a couple of questions in the chat. So for the first one, how does the drone localize itself when the Aryk tag is obstructed or not visible?
Okay, I can take this one. So basically, if you have a scenario where the person, I guess, changes direction suddenly and might walk in front of the Aryk tag, the drone will use dead reckoning by taking the last frame and trying to use the internal speed estimation to calculate its position over that time. However, this does present a bit of a problem because the Tello's understanding of its own speed is rather inaccurate. I think there's around a 4% error in its internal speed estimation, which when compounded could get unruly pretty fast. But with higher quality drones, with better built-in systems, the accuracy would increase and the quality of our dead reckoning would also increase. So, yeah.
Great. And then one final question. actually, we'll lump them together because there's two questions about YOLO. So first question is, what training set did you use with the YOLO, or did you use a pre-trained YOLO model? And then secondly, related to YOLO, how would you speed up YOLO in future iterations of this project?
Okay, so to answer the first question, we were using a pre-trained YOLO network that is trained on the Krauman dataset. I think there's a GitHub repo. I can put that in the chat if you would like more information about it. And as for how to speed up the YOLO, we're currently using the YOLO v5m dataset, YOLO v5m model, which is one of the larger and more accurate models that within the YOLO subset. But to speed up the project, we would consider using smaller models such as YOLO v5n or YOLO v5s, and that would drastically increase the YOLO's inference time.
Excellent. Thank you so much for your presentation. It was a wonderful job. And at this point, this concludes all the presentations. Your instructors have just a couple quick words of thanks and congratulations. So we'll go down the line, starting with Remaisa.
Hey everyone, it's been an honor to work with you all this summer. I'm really proud of everyone and the amazing final projects that you guys have worked on with ROS and Python and many other libraries. And you guys have definitely come a long way since week one, from setting up your Tellos and your virtual machines to making them fly autonomously. I really can't wait to see you guys take the skills that you've learned here at BWSI and work on impactful applications and research in robotics and autonomous drones. And I'm pretty confident that everyone here will succeed in your future academic endeavors.
Ifweko.
So congratulations everyone on such amazing projects. As you know, you should all be so insanely proud of yourselves for what you've accomplished. You've shown so much creativity in each and every one of your projects, and the teamwork you've all displayed in support of each other was very admirable. So it was so great to see you all support each other and learn so much. And I really hope that you take all these experiences that you gained during BWSI to your college experiences and beyond.
Matt?
Yeah, I just want to say it's been an honor working with all of you, and it's incredibly inspiring how quickly you took to all of these topics, many of which were brand new to you, and you not only learned them, but you mastered them and put together these amazing projects. So thank you for the inspiration. It's been a lot of fun.
Aryk?
Just want to check my microphone's working.
Yep.
All right. Yeah, great job, everyone. It was a pleasure to watch the fruits of your labor. Thank you all so much for your hard work, determination, and curiosity. I'm very impressed with all that you have all done, and I hope that you learned something new and interesting this summer. It was a pleasure working with all of you.
And just to reiterate, wow. We are so proud of everything that you've put together. All of these projects, every single one of them, so very nicely tied together. Controls, machine learning, computer vision, and you guys did something fun with it. And that's what matters. So we hope that you had a wonderful time working with us. We had a blast, as always. There's a reason why a lot of us keep coming back to teaching, because it's a really joyful experience for all of us, and we love to give back. So thank you once again for being such wonderful students and for inspiring us as well. We truly enjoy what we do. Thank you to Joel and Lisa in the background who really helped make all the things work, got you your drones. We wouldn't be here without their support throughout the summer. So with that being said, for the very last time, thank you, UAV. You all have been wonderful, and we'll hopefully our paths will cross again some point in the future. But that's all we have for you today. So thank you so much, and congratulations once again.